spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent friends, it's valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew. Of the days we spent with you, all hail our own Purdue. Wedded after
This is
years,
our
returning
fifth
alma mater
school,
back
if I
to
remember
you.
correctly, which marks the 5th year of our Quantum Science Center, one of the National Quantum Initiative Centers funded by Department of Energy, and we will hear more about our Quantum Center and quantum research. But I just wanted to welcome you first by saying how honored and privileged I am to have been working with all of you and actually interacting with this incredibly talented crowd of people for these years. I just wanted to go back in time, and that was the beginning of the center. I think even maybe a year before we submitted, and I was approached, and people asked me if I want to be the workforce development lead. And I said, you know, I'm just a professor, I do research. I don't know what to do. I don't know. I can take up the job, but I have no idea how it's going to turn out. And I have to say that this has been one of the most exciting and rewarding adventures for me professionally and just for me personally. And what I thought is that, well, I am a professor, but what I do, I teach and I interact with young people, and that's what I enjoy most. And this is the most rewarding part of my profession, to see young people grow. One of the important things in growth is to give initiative to young people, and that's exactly what we've been trying to do in QSC. Grassroots activities are the strongest and the most active ones. So we, from the beginning, have a very active group of students and postdocs. And again, I would like to start by thanking the PGA team for putting this together. Well, of course, together with Purdue Quantum Science and Engineering Institute team and Purdue conferences. But this event is yours. I'm addressing students and postdocs, and please make sure that you take most from this conference. And I still remember my first quantum summer school that Professor Polzik was teaching back in Denmark. And that was always such an amazing experience. And that's a time when you learn, when you network, and you make connections for life. So use this opportunity to connect to researchers, to professors, to scientists, engineers from companies, from national labs, and also connect to your peers. And as I said, build these connections that will last a lifetime. And have fun. So with that, I am going to introduce our director, our Quantum Science Center director, to give more quantum opening remarks for the school, Travis Humble.
Hey, thank you, Sasha. And hello, everyone. It's a pleasure to see you here. As Sasha said, I direct the Quantum Science Center, which is one of the Department of Energy's National Quantum Information Science Research Centers. This is part of the United States National Quantum Initiative. And what I wanted to emphasize, in addition to everything that Sasha said, the amazing experience that this provides, the intellectual breadth that this provides. I was looking through the program. But the most important thing for me is that you all, as a generation of scientists, are in some sense the first generation to have the attention and the support necessary to create a next generation of quantum science and technology. A lot of what we're currently doing within the Quantum Science Center is based on the remarkable achievements that have happened over the last several decades, the pioneering experiments, the breakthroughs, both in the understanding of quantum information, but then also its application to new areas. But I honestly believe we're at a very early stage in that development. What we're going to need are people who are exposed and motivated by these ideas to pioneer new approaches, new applications, and new domains in science and technology that, frankly, we haven't even thought of yet. I know that's a lot to put on you on the Tuesday morning at 8 o'clock or 9 o'clock, but that is exactly what we're thinking about, is that by working with you throughout the week, we can help take the first steps towards creating that next generation of ideas. So I want to extend my thanks to Sasha, to David, to Mike, to everybody who put this event together, especially to the PGA. I know yesterday we had the pre-orientation or pre-gaming, as I like to think of it, for this week's activities. I know that's a lot of work, and I know all of our speakers that have come to participate this week are taking time out of their schedules because they recognize the significance and importance of working with you as well. So with that, I'll hand it back to Sasha and thank everybody again for the opportunity to see you and to talk with you throughout the week.
Thank you very much, Travis. We are actually rolling into our first scientific session, and I'm actually turning it over to PGA. And they are going to be the ones who will be chairing and moderating the scientific part and introducing Ryan, who is the boss here, by the way. If you have any questions, Ryan is here. Thank you.
All right, thanks, Sasha. Okay, so we're actually going to have Mark moderating the first session, and we'll go ahead and get started. So,
thank you. So I'm Mark Illa, I'm a postdoc at University of Washington. I'll be moderating the morning session today. So for our first talk, we have Michael Marfram. So he's the director of the Purdue Quantum Science and Engineering Institute, and is the Bill and D. O'Brien Distinguished Professor of Physics and Astronomy, Professor of Materials Engineering, and Professor of Electric and Computer Engineering at Purdue University. He also serves as Scientific Director of Microsoft Quantum Lab, West Lafayette. He and his team develop new nanoscale electronic devices to explore fundamental aspects of topology and strong electronic correlations. In 2020, his group reported interferometric measurements of anion braiding, and he now works with Microsoft Quantum to develop scalable quantum hardware leveraging the novel properties of anions. So now he will talk us about universal anion tunneling in a chiral Luttinger liquid. Please.
Thank you very much. Anything here? Oh. Oh, thanks. Can I go? Just going. If it goes into the slideshow, yeah. Good, excellent. Thank you very much. Thank you for that nice introduction. My name is Mike Manfra. I also want to take the opportunity to thank David and Sasha and Jennifer for organizing this event. I actually had nothing to do with it. I just show up. So they did all, along with the students, did all the hard work, and putting this together takes a lot of organization. So I want to give them a heartfelt thanks. So one of the primary motivations for our particular Quantum Science Center out of Oak Ridge was to explore topological phases of matter and to see how topological degrees of freedom might be useful for quantum information processing. And to do that is a rather lofty goal, in the sense that we want to use the inherent built-in protection afforded by topology in order to build more robust quantum systems, particularly protecting them down at the quantum plane level from decoherence. Now, that sounds very nice, but how do you actually do it? And what systems are most amenable to this type of exploration are important questions that the Quantum Science Center is attempting to answer. I'm going to give you one particular example. in my estimation, a particularly useful one. It's a model system, the fractional quantum Hall effect, particularly in aluminum gallium arsenide heterostructures, is sort of the paradigm of a topological phase of matter. And why this is useful is because over many years, the efforts of many different groups and pioneering efforts, we've gained a significant amount of control over this system so that we can build complicated mesoscopic devices in order to probe the system's properties, in particular its topological properties. So to say if a phase is topological is all well and good, but how do you actually access the degrees of freedom that are purported to be topological? That's the story I'm going to tell you. Now, the reason I think it's interesting for a broader audience, and especially students, is I hope it acts as an example, a model of the techniques and thinking about how to approach problems with topological phases that may have applicability to other systems, be it quantum spin liquids or fractional churn insulators or topological superconductivity. So I'm going to talk about a very specific example that I work on, but the point is it doesn't, the techniques and the approach we use is not just applicable to fractional quantum Hall physics. The following talk will be given, or one of the talks coming up by John Watson, who works on another topological system. And you'll see, I hope, some commonality in the approaches. Okay, so I have this title, Universal Anion Tunneling in a Chiral Luttinger Liquid. So what does that mean? Well, the objects that we're interested in these topological phases, particularly for quantum information process, go by the name of anions. They're emergent degrees of freedom that are neither bosonic nor fermionic. They have unique quantum statistics, and they can come in a variety of flavors, the first being broad categorization between abelian and non-abelian anions. The ones I'll talk about primarily today are abelian anions. All abelian or non-abelian means is whether if you perform two operations, do those operations commute or not. John Watson will tell you about another flavor of anion, Ising anions, which are the simplest example of non-abelian anions, but the techniques we're talking about are general. Okay, so I want to introduce the team. The people who actually do the work are the students and postdocs. Ramon, Aditya, and Tame are current members of my group who are all contributing to this project, and it's really their work I'm presenting. Okay, so the fractional quantum Hall effect occurs if you take a two-dimensional electron gas, where you have electrons confined to move just in the plane, the xy plane, but not in the z direction. They can be through size quantization in the system I use, aluminum gallium arsenide heterostructures, or it could be a truly 2D material like graphene. Regardless of how you make it, the salient feature is that the electronic motion is only in the plane and not in the third dimension. And what I show here, is there a laser on this thing? Evidently not. Well, anyway, here is some transport data, bulk transport data. All that means is I have a sample, I attach some ohmic leads to it, and I measure the various parts of the conductance matrix. So this is sort of what the quantum Hall effect looks like in a modern sample. The blue trace is the Hall resistance. That's the voltage that builds up across the sample perpendicular to the direction of current flow as you increase the magnetic field. And the red trace is a longitudinal resistance. And what you see in a modern sample at very low temperatures here, 10 millikelvin, in the longitudinal resistance is this really spiky behavior. Most of the time, the resistance is zero. The longitudinal voltage drop is zero. It's interrupted by these very high spikes of resistance as it transitions through insulating phases. And the Hall voltage, as you may know from your basic classical physics, E&M, should be a straight line. It's basically proportional to the magnetic field and inversely proportional to the density of carriers. And classically, we should just see a very boring behavior, a straight line, and for the RXX, the longitudinal voltage, it should be independent of magnetic field. Of course, that's not what we see in real life. I'm actually going to grab a laser pointer, my own laser pointer. You see this linear behavior in RXY punctuated by these flat plateaus, where the Hall resistance is quantized to amazing precision, 10 decimal places, in multiples of R is equal to H over E squared, two fundamental constants of nature. And that quantization, which you see in the bulk transport properties, is what is the signature, tells us that something very interesting is going on. Now, the integer effect is due to quantization of electrons, fermionic excitations, nothing too interesting. But these fractional filling values, where nu equals 2/3, 3/5, 1/3, nu is the filling fraction. That's the ratio of the density of electrons in the 2D gas to the density of flux quanta penetrating the system. So at nu equals 1, I have 1 flux quanta per electron. At nu equals 1/3, I have 3 flux quanta per electron. But you see similar phenomenology at these fractional filling factors. It looks like the integer effect with precise quantization, but it has a much different origin. It's due to strong correlations and being in specifically a topological phase. Now, in modern samples, you can study all the wiggles you want. If you're interested in wiggleology, you can look at all the multitude of fractional states that develop. And there are ones that are interesting. Most of these are abelian. They're hosting abelian anyons. There are also states like the even number 5 halves that's seen here, where the excitations are believed to be non-abelian, and we're working hard on this state right now. But, you know, given the level of control of disorder and fabrication in this system, it's an exquisite playground for testing some of these fundamental ideas of how do you probe anyons directly, not through inference or, you know, a bulk transport experiment typically is not enough. It tells you something interesting is there. It's a good place to look, but to actually make progress, you have to do more. And so what you need is a blueprint. And this blueprint or device model was laid down a long time ago by some of the titans of the field, Kivelson, Sondhi, Xiaogang Wen, and also by a young graduate student at MIT named Claudio Shimon. And they had a proposal. They had this idea which we now call a electronic Fabry-Perot interferometer. Basically, it was a Hall bar with quantum point contacts that bring edge states into close proximity so they can scatter. There's a couple of them, and if we're in a coherent transport regime, we can do interference experiments. And so this is the electronic or anionic version of the famous Fabry-Perot interferometer from optics. Now, the world's a little different. In gallium arsenide, photons, as you know, are non-interacting bosons. We have a very different system, but the analogy holds quite well. And what they proposed here is interesting. They say, in this device, we can study quantum interference due to strongly correlated system. Today, we would call that a topological system. The device provides a mean of measuring fractional charge, fractional statistics, and distinguishing between Fermi liquid and Luttinger liquid behavior. And this is a really prescient statement. They didn't state it this way back in 1997 when they did this, put this paper out. But basically, this is a model, a blueprint for measuring the topological order. If you can define 3 parameters, the fractional charge, the anionic statistical angle, and something called the scaling dimension of the theory, or tunneling exponent, which is the bulk of what I'll talk about if I ever get there, you fully characterized what universality class your topological phase belongs to. So this is a powerful statement, at least in theory. It's a topologyometer. at least in principle, okay? And we're going to see, this was in 1997, how well this holds true. Now, I should just mention as a plug, that young graduate student is now a senior, well-established theorist, and he'll be joining the physics department next semester, Claudio Shimon. And so we're going to be lucky to have him joining our efforts. Okay, so the excitations of the fractional common Hall effect are anions. They have fractional statistics and fractional charge. So, oops, that was wrong. So, you know, the theorists have told us that the charge is fractional. Laughlin told us in his original explanation of the fractional common Hall effect in 1983 that to have a quantized state of nu equals 1/3, you must have a fraction charge. But in reality, it took 15 years for advances in experiments, quantum shot noise measurements, samples to improve, devices to improve, before two groups were able to use quantum shot noise so that they could actually verify the fractional charge. Anionic braiding statistics was also known to the theorists in the early 80s. Berg-Halper and Wilczek and others had demonstrated, at least theoretically, that in addition to a fractional charge, these excitations had fractional statistics. Now, it's only been in the last few years that my group and others have been able to demonstrate directly that this is indeed true. And so a little bit of the story I hope you'll come away with is that, you know, that there are great theoretical ideas, but their implementation in practice often takes a long time. And the work of many groups, not just my group, but we built on the efforts and learnings from others. And so that's the fun part for being experimentalist. Okay, so what do I mean exactly by fractional braiding statistics? If I have a localized quasi-particle, oops, some of this is not working, and I wrap it around another and bring the system back to the original state, you say, well, that's boring, you're just in the same state. But actually, for anions, you build up an observable, non-trivial phase, a phase factor of 2 pi over 3 at nu equals 1/3. And that has observable consequences. That's been the subject of my talks over the last few years. Now, what I haven't talked about in the past is that this part that if you have measurements of the fractional charge, the fractional statistics, and this scaling dimension, or tunneling exponent, which I'm going to talk about right now, you fully parameterize the topological order. And this is something that I think we want to think about applying to other systems, not just fractional common Hall states, okay? So you're going to have to take my word for it or see some of our papers that this is a check, fractional charge is a check, fractional statistics is a check. The question mark is about the scaling dimension. So what I haven't said is these topological phases of fractional common Hall effect, not only do they have bulk excitations, but interesting things happen at the boundary. To go from a topological phase to a trivial phase necessarily implies very interesting edge physics. There's a bulk edge boundary correspondence that's well known in the field. So if I have a topological phase up against a trivial phase, I necessarily have interesting physics at the edge. These are called edge modes in the fractional common Hall effect. As it turns out, there are 1D strongly interacting electron channels or electronic channels circulating around the periphery of the device. They're gapless. In the bulk, the system is gapped. At the edge, it's gapless. So these edge modes, these one-dimensional channels, are perfect conductors. They move along the edge without scattering. They carry a unit, a quantum of conductance. If it's an anion and it has charge E over 3, it carries E squared over 3h, okay? And they're described by a chiral Luttinger liquid. They're strongly interacting gases, if you will, of electrons, okay? In one dimension, the system is unstable against small interactions. The system is singular. It's not perturbatively related to, say, a Fermi liquid. It's quite different and has very different characteristics. And in fact, it has some universal scaling properties, at least that was what Zhao Gangwen taught us in the early 90s, that tell us how the nonlinearities in this system should behave. Remember, if I just have a conductor and I apply a voltage, the current that I get out of it should respond proportionally. It's called a resistor. So if I measure, say, a differential conductance, I should get a straight line, parameterized by the ohmic resistance. These are not ohmic resistors, as we're going to find out. How do we measure that? Well, we bring these 1D channels into close proximity using E-beam lithography and surface gates to put them in close proximity so I can have backscattering from one edge to the other. Here in the bulk, when they're separated, there's no scattering. But using these gates, I can bring two edges counterpropagating into close proximity and then do some weak backscattering. I can also go into strong backscattering. The tunneling conductance, how the anions bounce from one edge to the other, is governed by a universal scaling function here. This is the result from Xiaogang Wen. This tunneling conductance depends only on fundamental parameters and this tunneling exponent g, which is quantized in the, at least theoretically, in the quantum Hall regime. Okay, so it depends on a function of temperature and the dimensionless ratio between source drain bias and kT, the temperature. So if I know the effective charge, I don't need to know any other microscopics. That will allow me, by looking at the tunneling conductance, to see if we really do have exponential dependence, okay? It's not a resistor. This would not have exponent like that if it were an ohmic resistor. Okay, so that's what we're going to try to see, all right? Now that universal function looks a little bit scary, but this is an analytic expression for the tunneling conductance in the weak backscattering limit, okay? And again, there's no microscopic parameters that I need to find out in here. Well, there's one, T0, but that's a function of the junction. But it just depends, on X. X is that ratio of voltage to temperature, and this tunneling exponent G, or at least it should. Okay, and this is, you can plot this in Mathematica or whatever your favorite plotting routine is. This is what the function should look like as a function of temperature, assuming G equals 1/3. Now I'm working at the 1/3 fractional quantum Hall state, so the prediction is that that exponent is quantized to 1/3, and this is what you should see. Now, we can measure that in our system, and I'll show you how in a moment. I need to move on. Now, you could ask, okay, the theoretical arguments were made in 1997. It doesn't look like it's all that complicated. Why have you been goofing around for so long? Why has it taken so long? Well, the devil's in the details. The experiments, the real world is described by complicated physics. Models are an approximation that we use, often a very good approximation, that are simplified enough that we can actually solve the equations to do something analytic. What it turns out is that to do the interferometry and see the anionic statistics, we had to build a novel header structure in MBE, molecular beam epitaxy, for these layers of semiconductor. By the way, John Watson, who's one of the speakers, helped me build this system many years ago. So what we did is we have a primary quantum well where our two-dimensional electron gas resides, but then we build in situ, two ancillary layers of two-dimensional electron gas. Their purpose is to screen the long wavelength part of the Coulomb potential and make the confining potential at the edge very sharp. It makes our band structure and device more complicated, but it's a small price to pay for the advantage of sharp confinement at the edge and screening of these Coulombic effects, okay? What we gain is that we have very sharp confinement at the edge. This model that I showed you of these chiral edge modes and that scaling function are built on an assumption of sharp confinement, meaning that the potential goes to zero, or the electron density at the edge goes to zero very rapidly. If it's not the case, you get all sorts of interesting but secondary physics. So when we were designing these things back in 2018, 2019, we saw that we could get much sharper potentials, okay? And this work is built on the efforts of these three people here who did the MBE growth for these particular structures, and Jimmy Nakamura, who helped me design them and make the first measurements of braiding statistics. Okay, so The take-home message, why am I telling you all this? Sharp confounding potential is important to see the properties of chiral edge modes. We have these screening wells, and it's like shining a flashlight through a stencil or something, where all the divergent rays get blocked out, and it's just a precise map onto the two-dimensional electron gas. And if you look at the conductance, say at nu=1, this is the integer state. You see perfectly quantized conductance as you start pinching down the QPC, and then a rapid decay. And that's exactly what you want. Historically, it's looked quite different. You start at this is nu=1, this is nu=1, and then you see all sorts of schmutz and stuff, and then intermediate plateaus. And this is just a signature of soft confinement and edge reconstruction. Okay, I know I need to move on. So what's our real device? Well, we've been building these interferometers for several years to measure statistics. Now we can take these interferometers and basically operate them in the simplest mode possible. We turn off most of the interferometer, so there isn't actually coherent interference, and we use just one of the QPCs as our way of backscattering from edge to edge. And if I do that, the current flows along this edge. It's weakly backscattered to the other by this QPC, but most of the current goes out to the drain. And if I look at the properties as a function of magnetic field, you can see that in this little region, it behaves much like the bulk. What I'm showing here is the voltage drop across the QPC in a certain limit, and the bulk transport, and they overlap. Now, we measure this thing in this really ancient and rare instrument. It's called a wet dilution refrigerator. This is something that I actually brought with me when I moved to Purdue 15 years ago from Bell Labs, and it had been used for another purpose at Bell Labs. And John Watson, my first graduate student, one of his tasks was to reassemble this thing from parts. And you can see we're using the latest technology for this. Use a fine wood grain gas handling system. Vibration isolation system is the absolute latest and greatest. This is what the device looks like. Doesn't look so pretty, but that's what it looks like. But this system works really well. So evidently no one liked those jokes, but all right. So here's the conductance at nu=1, perfectly quantized. Again, this is just an integer state, electrons. And then I measure the differential conductance. Okay, that quantity that I said was so interesting. Well, look what it is. It's a straight, flat line. What could be more boring than that? The differential conductance is flat. There's no slope. What is that, students? Linear relationship between I and V. It's an ohmic resistor. It's a perfectly boring Fermi liquid of electrons, okay? So the fact that we measure this flat differential conductance is a signature of we're dealing with just boring old electrons, and they obey Fermi liquid theory, which is a good sanity check. If I got a different answer, I'd be in trouble. Okay? So now we change from the integer states, but to these fractional states, which are in principle topological and support anions. Now, the zero bias conductance is a little bit more complicated. It starts out at 1/3, as it should, but there are these features that you see before you see complete depletion. This is residual disorder. It's a fingerprint of the mesoscopic disorder. We often see this at fractional state instead of just going straight and then flat down. Nevertheless, besides having a few little, you may colloquially term them resonances, we see very sharp decay of the conductance, meaning again that the confining potential is sharp. So all of my measurements I'm going to talk about are in this blue region, where we tune the backscattering in order to look at this differential conductance and see if it matches with the theory of when. Okay? So here's what that differential conductance, remember at nu=1, I had this straight flat line boring. This is clearly not a resistor. Okay? So this is in the middle of the nu=1/3 plateau. The electrons are very cold, about 34 millikelvin, and you don't see a flat straight line. You see highly nonlinear behavior. On the right is just a 2D map in source drain bias and QPC voltage. That's how much backscattering we induce on the x-axis. And the SD, voltage source drain, is just a finite source drain bias we apply. And we have this color map. Now the dashed green line is the green line that we show in the waterfall plot on the left. Okay? So remember, there is a functional form that's predicted by theory that I can try to match my data to. And I know various parameters, and I try to fit this data. And lo and behold, this is the Wens function. We're fitting this theoretical function in the weak backscattering limit. Again, no microscopics in here other than the transmission of the QPC. And we extract a scaling dimension or tunneling exponent of 0.334 to the limit we can measure it. Now, the prediction is 1/3, 0.333. This is, we took as very good evidence that the anions in the 1/3 edge mode are behaving as they should for a chiral-Luttinger liquid, okay? Now, I'm gonna rush through this stuff. I'm way over, I assume already, but we can tune things. I have this universal function, so I should be able to see scaling behavior. I should see scaling collapse. So I can measure in a variety of ways. I can fix the temperature and vary the transmission. That's what I've already shown you. We sit at one magnetic field, one electron temperature, and basically change how much we're backscattering the anions here. Or I could sit at fixed transmission and vary the temperature and look at the temperature dependence. So there's three basic parameters: the bias voltage, the electron temperature, which I can measure in situ, and the transmission. And I do, or the students do, and I just look at the data, a bunch of measurements of this sort. And here is scaling behavior. We measured here the tunneling conductance as a function of the dimensionless ratio, temperature over T0, that I told you about earlier. If I put it on a log-log plot, you clearly see a linear behavior over a couple of orders of magnitude. That's a signature that you actually do have a good exponential dependence. We see the scaling behavior. The red squares are the measurements. And to see how constrained this is, if we just change that parameter, that scaling dimension, from 1/3 to 0.4, you get the black dashed line. Clearly in variance with the experimental points. If you change it to 0.3, you get the other line beneath it, a little closer to the data, but clearly not expressing the exact relation. So I can't say it's kind of 0.3, somewhere between 0.5 and 0.2. It's really close to the quantized value. We can do this in a number of different ways to convince ourselves. We can measure it at different temperatures and look at this scaling behavior again, and again, the agreement is pretty good. So what everyone does when you talk about universal functions and scaling, you try to make a plot where you collapse it onto a dimensionless scaling variable. So if I do that, where I plot the reduced conductance as a function of the source drain bias over the temperature, here it is on a linear scale, all of those many curves that I show you collapse onto the same curve. I can do this on a log-log plot, and these are all different measurements at different temperatures. The data plotted in this way, and you can't really see it, but there's a theory curve that goes right through it. So this was really the first demonstration of this scaling behavior for a fractional quantum Hall liquid at 1/3. There's been some interesting, I shouldn't mention, I shouldn't be so dogmatic about this. In graphene, Andrea Young at UCSB has done a very interesting experiment where he tunneled from an integer state, nu equals 1, into 1/3. That's tunneling of electrons, and it also showed scaling behavior. It's a very nice work. Here we're tunneling anions, which is the important point. These aren't electrons that are tunneling, they're anions. And you only get this behavior if you are tunneling via anions. So how robust are these results? Well, I showed you some scaling behavior. Here's another device, a completely different device where we go to 1/3. What I want you to concentrate on is just up here at 1/3, where it's quantized both in the bulk and in the device. We measure this scaling dimension or tunneling exponent as a function of magnetic field across the nu equals 1/3 plateau. And it's not like I fine-tuned the system to get this 1/3 value. I can move the magnetic field over a finite range, almost 1 Tesla, and it stays quantized. That's exactly what theory tells you. Why this is useful and unique is that it's really quantized. It's not a fine-tuned parameter. Now, eventually, way out in the flanks, it will start to deviate, but that's exactly what you expect. So the quantization holds over a broad range on the plateau here, and I just emphasize that this is a completely different structure and device than the one I was just previously showing you. We can see how well this G holds as we tune the backscattering. Remember, the function I showed you was derived in the weak backscattering limit. So it holds really well when we're in the weak backscattering limit. Now, as we go to stronger and stronger backscattering, it starts to deviate. And so by the time we get to 0.7 or so, we're sort of out of that 5% window where it's quantized. This is not a failure. The theory is only good in the weak backscattering limit, and then there's a crossover to the strong backscattering limit. So the fact that we stay within 5% over this range is more or less what you'd expect. And we expect this to deviate as we move away. You could have asked, for the experts, well, you had these little resonances or schnicks in the data. Maybe that's affecting things. Well, again, we went to another device that has a really strong resonance, and then we measured at 3 points. Okay? These are all the same backscattering, they're the same tunneling, but clearly they're different points in the phase space. And you just have to take my word for it, it still fits. So as long as we're at the same value of backscattering, having the presence or absence of these features in the zero bias data, at least empirically, seems to have little impact, which is good, otherwise we'd be in trouble. All right, so I'm going to conclude, and hopefully I'm going to make a rather strong statement, and you're free to challenge me on it. We have a paper online about this. The conclusion is these findings indicate that the classification of the topological order responsible for the fractional Comm Hall effect can be fully characterized by a sequence of measurements in a Fabry-Perot interferometer. That's important. One device, one cool down, fully parameterized. It's not like it's a 3-day experiment. It takes you a long time. That one device can tell you what the topological order is in this phase that you're interested in, okay? I think we've now, with this last piece of the puzzle, demonstrated that. We can measure fractional charge, fractional statistics, and hopefully I convince you that we can measure this tunneling exponent or scaling dimension in this device. Now, this is a general recipe in some ways. We use it in the fractional Comm Hall effect, but analogous models should be available, and people are working on them for quantum spin liquids, and there's people in QSC, Gabor Hazles is working on, and Jason Alisea working on interferometry for quantum spin liquids. There are similarities, there's some differences, but hopefully you get a sense that this is a doable thing, and it can be used as a tool for future investigations. We're obviously going to look at non-abelian cases. You'll hear, I think John will tell you a little bit about interferometry with Majorana's Ising anyons. So that's my meta message, is that we now have techniques that we can use to say very explicitly what type of topological order we have. So thank you for your attention.
Hi, so I guess maybe something I'm a bit confused about is the exact role of the Fabry-Perot interferometer. It seems like you're measuring a series of just resistances and currents. So as far as I understand, Fabry-Perots give you some sharp bandwidth in the frequency domain. How does that relate to?
Yeah, well, I didn't have time to concentrate on that. So the Fabry-Perot is passive in the measurements I was talking about. Sure. I don't know, I probably said it too quickly. I turned most of it off to do these tunneling experiments because there's no need for coherent transport throughout the interferometer. But in the 2 experiments that lead up to it to measure the fractional charge in the anionic phase, it's absolutely crucial that I have coherent transport and interference inside the chamber. of the interferometer. The way you measure the anionic phase is to measure shifts in the interference phase. That's another talk, and I can tell you more about it during the lunch break, but that's a prelude to the measurements I was making today, where the interference and the fact that it is a coherent process are central. Here, I gotta tell you, you're just like, oh yeah, we can do this too at the end, and turn off most of the device.
I see.
Okay, so the Fabry-Perot is essential to measuring statistics and the charge determination that we did.
I see. So essentially, like, it's like you're forming a cavity within.
There's a cavity,
Yeah.
and your beam splitters are the two QPCs. The edge mode comes in, you weakly scatter some. Most of it goes through in the chamber. Then there's a second QPC, and you weakly scatter there. But there's a circulation of current through the interferometer. And if that's coherent, it recombines with the current that was scattered at the first QPC, and the relative phase shift between those two is what you measure.
Okay, thank you.
Yep.
Another question?
There was another one. Yeah.
Hi, thank you for the very nice talk. I was wondering how you can see, or maybe not see from the data, if these anions are abelian or non-abelian.
Yeah, good question. So again, that's a different talk, but we will, and we're working on right now, take our interferometers and operate them at nu equals 5 halves, which is a putative non-abelian state. And the picture of what interference will be is distinctly different for the abelian case and non-abelian case. And in the non-abelian case, I should show it, but I don't have it in these slides. In the abelian case, you just get this barbershop pole in a 2D plane, magnetic field versus plunger voltage, conductance plots, where you see these barbershop lines of constant phase with negative slope. That's the classic AB pattern. If they're non-abelian, a prediction of theory is, depending on the parity of the, inside you have two E/4 quasi-particles that share a Majorana mode. That's either, the fermionic mode is either occupied or not, and depending on that, the interference pattern will either be visible or not visible. So it's like a blinking. The pattern will turn on and off depending on the configuration of the non-abelian anions inside the chamber. So there's a very clear and distinct prediction for non-abelian anions versus abelian anions. Now, for the abelian case, we actually are able to extract the abelian phase from the discontinuous slips that we see in the phase pattern. And it's not like they can take on any value. They have a very precise value associated with whatever state they're at. So in the abelian case, through FFTs and then just looking at the discrete phase slips, you measure the anionic phase directly. So the answer is, we don't have the data yet for non-abelian case, but there are distinct predictions between abelian and non-abelian.
Great, thank you.
Yep, good question.
One last question?
Thank you for a beautiful talk. If you could say in one sentence, what is the main reason why people have not measured non-abelian anions yet in these systems? What is the
Which
major
system?
challenge?
In
These
fraction-
systems, in the
be
5
precise,
halves
that
state.
in 5 halves. Yeah, because we do, there are, okay. In 5 halves, there is, it's a solvable problem. We went to 1/3, the abelian state first, because it's the strongest. What does that mean? It has the largest gap, excitation gap. It also has a simplifying feature that there's only one edge mode, one circulating charge edge mode. Now I go to 5 halves that occurs at higher filling, so necessarily much lower magnetic field. The intrinsic bulk gap is significantly smaller. So the biggest gap that you'll get at 5 halves is like half a Kelvin, whereas at nu equals 1/3, it can be 5 to 7 Kelvin. So it's an enormous difference. So all the energy scales are compressed. The second feature is that there are multiple edge modes at 5 halves that can complicate things. It's not a fundamental problem, it's a technical problem, and I think we and others, and just not me, but we have some good plans on how we're going to overcome that. It's a solvable problem. If we don't do it in gallium arsenide, it'll certainly be done in the 2D systems. Graphene has a tremendous, in some ways it has advantages, in some ways it has disadvantages. One of its tremendous advantages is that it can have much larger gaps. What Andrea and Philip Kim and all that, what they do is they tune the density high and then they just crank up the magnetic field. So they'll measure 5 halves instead of at 4 Tesla where I measure it, they'll measure it at 18 Tesla, where the gaps are much bigger. And so if it's not done in this particular system, I'm positive it'll be done in the next few years in the 2D material systems. So it's a race.
Thank you.
Let's thank Michael.
Thank you.
So our next